Hey, what's up, guys? Today let's look at the Lintcode problem number 17, subsets. Subsets actually is very similar to the previous ones like permutations. They are just using the different strategies. So let's look at this problem. And for a given collections, for example, 1, 2, 3, then we need to derive all of its subsets. Its subsets has 3, 1, 2, 1, 2, 3, 1, 3, 2, 3, 1, 2, and empty. So how do we do this? Before we jump into the coding, and we need to know using what strategy we can, figure out this problem. So still, we're going to just use some graph to demonstrate this. So I have a graph here. Before we do that, we need to know what is the subset. This is what I got from Google. A subset is a part of a set. For example, if our set is 1, 2, 3, 4, 5, a subset is 1, 2, 3, because 1, 2, 3 is part of the subset. So I also give you another definition for us to easily figure out this problem. The subset actually is the ways how we select the elements from the given collections. How many ways are there and how many subsets will be there. I have a graph. So this is the given element 1, 2, 3. So we try to select the elements from the given collection. And when we are facing this 1, 2, 3, we can treat 1, 2, 3 as the candidates. We can choose, every of them. Choosing different elements will give us different subsets. So here, first we choose 1. After we choosing 1, then we'll have 2 and 3 left. So here we choose 2. After we choose 2, we have 3 left. So here we choose 3. Because 3 is the end of the collection. So this layer is done, so we just do the back tracing. We go back to layer 2. In layer 2, we actually have candidates 2 and 3. We tried 3 here, and now we're going to try we tried 2 here. Now we're going to try 3. So we get the a subset of 1, 3. 3 is the last element, so we just go back. We back tracing to the layer 1. When we are in layer 1, we have 1, 2, 3. We tried 1 here. Now we're going to try 2. We choose 2, and we only have 3 left in the next layer. So here we can only choose 3. 2 and 3, we got the subsets. Then we all the way go back tracing. We try 3. So after this, we tried every element. So this is done. But meanwhile, we need to know that there is a special case, which is that we can choose nothing from this collection. So we have the empty set. So this is our whole solution tree, or you can call it searching tree. Each tree node is our answer subsets. You can see we have 8 nodes, and they form our answer subset. By looking at this problem in a mathematical way, we know that for a given collection, 1, 2, 3, we have 3 candidates. But for each candidate, we can have 2 options for them. We can choose them, or we don't choose them. So each one, we have 2 possibilities. So in the end, the total solution number will be 2 by 2 by 2, which is the 8. By looking at this graph, when we choose one, we'll always just go deeper, then we back tracing. So this is the typical DFS. So this is our analysis part. Let's see our coding. This is the entrance. This is the input parameters, which is the array. So same thing here. First, we're going to do the parameter checking. If this is empty array, we just return this empty. Then we're going to just initialize the global result. We call our DFS function. We put all the answers into this result. In the end, we just return this result. Let's say our DFS, which is the search. the search function actually is going to take three parameters. One is the array. The other one is the subset. The subset actually is the local variable for this DFS call. Local variable is going to just save our local solutions, like each node, like node 1, node 2, node 3. So this is what this parameter is for. We also have the start index. Start index actually is confining the scope of this array. So when we were given an array, we're not just process everything in this array. We actually only process from the start index to the very end. Because this is the DFS search, this is recursive call. So typical usage of the recursive call is to make your problem, subproblem, smaller. So we use this start index to control our problem size until the problem can be resolved. Alright, so when we call this subsets, call this DFS, the first step we're going to do, we just add this local solutions to our global variable, which is our self.results. So every time we just add this node into our global answer, because each node is an answer. So that's why we're going to do this at the very beginning. So after this is done, we're going to just try the candidates. We try each candidate. And we started from this start index all the way to the end, because this is controlling our problem size. We don't want to, resolve the problem that has been already resolved. We're only focus on this start index to the way end. So first we try each element. We put this guy into our local solutions. Then we go one level deeper. So every time when it is deeper, we're going to just smaller size our subproblems. And once this is done, we're going to do a backtracing, which is we populate it out from our local solution, populate it out from the subset until we try all of our candidates. If the start index is 0, we actually have to try all the candidates in the given none. So this is our solution. So let's run it. Okay, looks great. It worked. So thanks for watching the algorithm. If you like it, and please subscribe. Thanks. Bye bye.